Hello students, hope you are doing well. In the previous class there is a disturbance, so we couldn't take our class in regular mode. As you can see here, we have covered almost all from the first and the second unit. Today we will discuss about the IC regulators, the line and load regulation, and short circuit protection. Okay, so today we'll discuss the IC regulators, line and load regulation, and short circuit protection. I couldn't find any better material for this in the textbooks, so I have to search a number of websites, and various websites have given differently, abruptly, and more knowledge. We doesn't require such knowledge. We want some basic knowledge where we can integrate all these three portions together. So on one website I possibly could find such things, so we will start from here. Okay, so here we first look around the line and load regulation, then we will carry forward towards the IC regulators and short circuit protection. As we know from this initial definition, the voltage regulation is classified into the line regulation and load regulation. Okay, voltage regulation means in normal sense we have to carry out constant amount of voltage in the output section. When we classify it into line regulation, the line regulation contains or it regulated when the input voltage changes, but the function of load regulation is slightly different. The purpose of load regulation is regulating the output when the load changes. Okay, so the term itself carrying its definition. In line regulation, output voltage is regulated when input voltage changes, but in case of load regulation, the output voltage being regulated when there is changes in the load. Okay, it is the basic definition given here. Now we come to the basic mathematics of line regulation. The line regulation can be defined in percentage or percentage per volt. Why percentage per volt? As we measured line regulation in a certain range of volt, therefore it is percentage per volt. So to define line regulation percentage, we take the ratio of the change in output voltage to the change in input voltage. Okay, we can multiply it 100 by for converting it into percentage format, or if it is percentage per volt, then we have to divide the change in output divided by original output divided by change in input into 100. Okay, so these are the two differences. We can apply any one of this with respect to the other. Okay, but the most suitable one is the second one, when we measure the percentage per volt. If the line regulation in percent per volt is nearly or greater than 0.10% per volt, means the output voltage changes in 0.10% when the input voltage increases or decreases by 1 volt. If it is 0.20% per volt, means the output voltage changes with respect to 0.10% when the input voltage increases or decreases by 1 volt. Okay, so this 0.10 volt generally describe us what is the amount of increase or what is the amount of decrease what we have to experience. Okay, so then comes to our load regulation. As the load varies, load means along the output. Okay, as you have seen that in maximum out devices the output load is connected through the resistance, that is R. Okay, R is generally appropriate to receive the load. Okay, so maximum cases the output is communicated through, or the load is communicated through resistance. As the load varies, means the voltage drop across the resistance varies, the load current changes. thus the output voltage also changes. Okay, as there is a voltage drop, so current changes, and current leads to change in output voltage. This change is independent to input signal. Okay, why independent? Because as we see in our circuit diagram of the regulators, as you can see, whatever changes happen in the output is not communicated to the input. Okay, so whatever input signal it can carry away as usual, it doesn't affect the output, or the output doesn't affect the input, vice versa. This should be reduced to a negligible value, because the load regulation is the solution of this problem. Okay, whatever value the input received is not affecting, or it is very negligibly impact the output circulation. So the load regulation is defined as the percentage change in the output voltage for a given change in load given change in given change in output voltage for a given change in load current or load resistance. Okay, but maximum cases we take into account the load current. The load regulation can also explain as in terms of percentage. So it is can be written as the percentage change in output voltage from no load to full load condition. Okay, so as you can see here, the load regulation defined as VNL means no load minus VFL divided by VFL means full load to no load into 100. So here also the example is given. If the load regulation is given as 0.05% per milliampere, okay, if it is 0.05% per milliampere, it means the output changes along 0.05% when the load current increases or decreases by 1 milliampere. Okay, if it is 0.10, obviously these things change to 0.10 when there is a unit increase in case of load current. Sometimes the power supply manufacturers, or who the producers of such type of line regulation or load regulation, does put the output resistance instead of load regulation, or they put the resistance in case of the load current configuration. So at that time when there is resistance, as I have already told, maximum cases there is current, but some manufacturers they put the load in a load resistance in case of the current factor. Therefore at that condition the load regulation can be calculated from the output resistance, that is the output resistance divided by the full load resistance into 100. Also it can be calculated by the above method and the below method, whichever is more suitable you can apply there. Then comes to our linear or switching voltage regulator. Okay, these two voltage regulators are generally operated for the line and load regulation. Okay, so these are the similar consequence of the line and load regulator. Only things are they inculcate the integrated circuit, that is the IC circuit, or we can say it is also available in IC circuit format. It is also available in integrated circuit format. Okay, so in case of linear voltage regulator, it is generally the series regulator and the shunt regulator, where the as you can see in case of your linear series voltage regulator, there is an error detector which is feedback the sample current towards the input again. Okay, as the sample circuit receives the output, the sample circuit slightly feedback some kind of current or voltage signal to the detector, and again the reference voltage it sends back to the input. So as you see in the figure, there is a control element between the input and output. The error detector detects error by comparing reference voltage with sample voltage. Okay, what are the reference voltage were given in the output, in the input, what is the receive in output, what is the difference? The difference is communicated by the detector. So here, as the diagram is show, as you can see the diagram, the basic operation amplifier series regulator is given. Here we see there is an IC, sorry, is an operational amplifier integrated with an transistor circuit. Is an operational amplifier integrated with an transistor circuit. So generally it is wholly operated or based upon the IC configuration. Here the same thing we can take in case of our transistor also, because transistor is helpful in the operation amplifier in carry away the error. So here the transistor is used as the control element and operation amplifier is used as the error detector. Okay, so the transistor uses the control element and the operation amplifier is used as the error detector. Reference voltage is generated by using a Zener voltage regulator. We've already discussed about this Zener voltage regulator in our previous classes. Okay, so here the output thus referred as the V out is nearly equal to 1 plus R2 by R3 VREF. That is the V reference. Reference voltage is 1 by 1 plus R2 by R3 times the output voltage. Okay, so this says that the output voltage is directly related to the reference voltage. Then comes to our the topic, that is short circuit or overload protection, which is specifically mentioned in the syllabus also. So if an excessive amount of load current is drawn across, obviously through the control element to the output. So if an excessive amount of load current is drawn, control element, what is the control element? That is series pass transistor, because transistor is behaving here as the control element, will quickly be destroyed. Okay, so excessive current if drawn through the output, then it is a high chance that the transistor or the control element suddenly destroyed or absorbed out. So to protect this kind of circumstances, or to protect the resistors there, a current limiting mechanism is required, a mechanism in order to limit the current. Such a protection method is shown in the below figure. Okay, as you can see here. Okay, in the previous slide, in the previous picture, you see that the only things remaining is here. Only thing in the previous picture is this much. The added portion was this. This is the added portion. There is a current limiter mechanism. This current limiter mechanism is handled by a resistance and a backward transistor. It is why called backward, because it is moving the current in opposite direction as per the Q1. The way Q1 moves the current, the other way Q2 behaves, or Q2 moves the flow. So this protection mechanism is called constant current limiting mechanism, or we can say that this is a series regulator with constant current limiting factor. So here the maximum limiting current can be drawn as IL maximum, that is load current maximum, is equal to 0.7 volt divided by R4. You can encounter this 0.7 volt by the 1 by root 2 factor, because you know when you divide 1 by 1 the root 2 value is 1.414, so you will get from here it is 0.707. you can get 707, so we can easily write it as 0.7. So after another method for overload protection is also called as our fold back current limiting. Okay, it is another one, is a fold back current limiting. This method is used in high current regulators. It is used in high current regulators where by the output current under overload condition fold back to a value well below its peak load current. It will prevent excessive power dissipation. Means whenever the device is a high current regulator, means it can have a tendency to hold large amount of currents. So whenever the load is burdened with high current, then some current is extracted along the output towards the error part, through the limitation mechanism, so that the peak value whatever maintained in the output reduces. For example, if the capacity of the device is holding around 5 ampere current, suppose it is 5 ampere current, it is already achieved the high value of 5 ampere. Okay, so some current around point 0.5 or point 0.6, some current is extracted, so that it can't breach the peak value, or it remain below the peak value. So it will prevent the excessive power dissipation, because we know that power dissipation is vi, p is equal to vi, the formula is p is equal to vi. Okay, so the more you current, the more power dissipation is, because voltage always remains constant, because it is a voltage regulator, so voltage is constant, but as the excessive current increasing, so it may leads to higher power dissipation. So you have to take care of these things also. Next comes to our linear shunt voltage regulator, because we are using a shunt or bypassing circuit there. Here you can see this is the shunt element or shunt mechanism provided here. So linear series voltage regulator have a transistor connected in series with the load to limit the excess load current through our R3 and R4. Here the transistor is not in series, rather in parallel to the load. Okay, rather in parallel to the load circuit. So in this case, in case of our the linear series voltage regulator, as you see in the previous figure also, the control element transistor is parallel to the load, as you can see from the figure also. A resistor is in series with the load, it is same with respect to this, but the main component part is here. Whenever the output voltage decreases due to the change in the input voltage or load current, sample circuit, you can see the sample circuit above, the sample circuit sense it and feed to the operation amplifier, and thus control element increases output voltage to ensure that it is regulated. Okay, so this is the important part. Whenever there is an increase or decrease, rather it can't be increased because there is a shunt mechanism, so it must be decreases. So whenever output voltage decreases due to change in the input voltage or load current, sample circuit sense it, because it is connected to the error detection mechanism, and feed the some part of it to the operation amplifier op amp, and thus the control element increases output voltage to ensure that it is regulated. Obviously, if there is a decrease in one side, there must be increase so that it can be balanced. Similarly, the sample circuit sense when the output voltage increases, it is in extreme circumstances or in exceptional circumstances beyond the required voltage. Again, it feedback to the operational amplifier, and the shunt regulate it again reduces at the juncture, so that this increase and that decrease is counterbalanced. Here, whatever shunt is used is generally less efficient than the series regulator. So the previous regulator is generally used where the transistor is in parallel operation. So here also the maximum current or the load maximum current is written as the maximum input voltage with respect to the resistance R1, the initial resistance. Okay, as you can see here, the initial resistance. Now comes to the switching regulator. Here, as you can see, in the previous parts we discussed about the series connection, the shunt connection, and the parallel connections. Both have the transistor as its element. These transistors are conducting all the times, obviously, because it has the functional all the way. Amount of conduction varied according to the changes in the output voltage or current. But in switching regulator, what we have to address now, in switching regulator, what will the control elements act as a switch. Okay, so in case of what makes it different, in switching regulator the control element is act as a switch. Okay, so great efficiency can be achieved with the switching regulator than the linear regulator. Whatever we can achieve through linear regulator, it is better to use the switching regulator, because it can makes the switching action like the on and off action frequently or controlling it in a good manner, so that dissipation power occurs only when it is required or only when it is in on position. Okay, so all switching regulators require feedback to control the on and off time. Okay, obviously there is the feedback mechanism we have to control during the on and off time, but the most important thing that it has a greater efficiency. As you can see here, it has a 95% efficiency. It is very helpful in maximum circumstances. Okay, so whereas linear voltage regulator acts as a variable resistor, generate heat and power. Okay, the switching regulators are designed for various power levels, and it can helpful in reducing all the impact by heat and power. Also, it can be used in minimum watt condition. Okay, so you can say that these are the efficiencies, or you can say what are the advantages of switching regulator than the linear regulator. You can write from here. So the switching regulators are truncated in three forms, that is step down, step up and inverting. Step down, step up, it looks like a transformer. You have already read the transformer, there is step up transformer, step down transformer, like that. So whenever the coil changes in any one of the part, whenever the coil is lie in the primary, it is the step, and less in secondary, then it is step down. Then if it is small in primary, large in secondary, then it step up, like that. The same function is nearly performed here. Okay, as you can see, in case of a step down transformer, it is also known as buck converter. So here the output voltage of the step down is always less than the input voltage. Okay, whatever voltage it has to be supplied in the output must be less than the input voltage, because its name signifies step down configuration. The basic control element is a high speed switch, because the switching and uncontrolled devices, it sends whatever the fluctuation carried away in the output junction and then adjust accordingly. So whenever the switch is closed, diode is in off position and the magnetic field of the inductor increases. Okay, so whenever the switch is closed, as you can see, whenever the switching element is closed, so the diode is off, obviously, because in off position there is no voltage difference. So the magnetic field, because as you can see that inductor is placed there, so inductor have magnetic field attached to it, because you know in 12th standard also how the inductor stores energy, because it's subject to different magnetic field fluctuations. It is half Li square, L is the coefficient of self inductance, and like that. So it stores energy. So when the switch opens, the magnetic field decreases. Okay, whenever it is closed, it stores energy, magnetic energy, but when it gets open or the switch is connected, it decreases. So it results in the constant current in the load. Okay, so at off position, it is conducing or conserving energy, leads to increase, but when the switch gets on, it will decrease, because whatever stored energy is generally dissipated out, which leads to the constant current balance in the load. Now the capacitor, whatever the capacitor here is given, which is grounded, makes the DC to nearly constant level, because it is the primary function of C, that it makes the constant supply. So it makes or leads to load resistance which is not very large, and makes the circuit completely forward bias conditions. Okay, the next is our step up configuration. Here a different element or different configuration used, because here we use the MOSFET here, okay, metal oxide semiconductor field effect transistor, MOSFET. Here the LC configuration behaves in order to facilitate the pulse through the from the transistor. The LC configuration here, the LC configuration, LC circuit, it facilitates the smooth pulse from the transistor, and it supply to the MOSFET accordingly. Sorry, it extract from the MOSFET and supply to the output, which is accompanied by the comparator. Comparator here is the operational amplifier, is the comparator, which compare the things. So more switching, because we know we already study what is the switching effect or switching arrangement. So higher switching frequency leads to higher switching action, and thus it may cause serious electrical noises, but we can minimize it by grounding all the components with respect to the differentiator. So we know that switching power supplies radiate harmonic frequency noise to nearby circuits, so they are well shielded or well protected and used in case of electromagnetic interference filters. Shielding is done by making a hollow sphere placed, so hollow sphere around it, so that it is behave like an isolated object or isolated arrangement. Here, in case of the step up configuration, as you can see, it is the output is equal to T, small t, divided by the capital T. Small t is the on time or the time required to first input receive the first input signal T on, divided by the total time. Total time is equal to T on plus T off, or to perform a complete cycle, or you can call it as a duty cycle. Okay. Next comes to the step of the same functionalities, just in case of reverse function. You can see from the figure here, the L is not directly connected, rather a diode is interfered here. A diode is interfered here. The variable pulse modulator is directly connected to the op-amp here. So here the basic control element is a high speed switch which works rapidly, and as we know the function, it senses the output quickly and adjusts the time of on and off to get the desired output. Okay. Next, our voltage inverter configuration. The same is generally bucket out because it have a activity of switching regulator, switching regulator, which produces an output voltage opposite in polarity to the input. So if we can analyze what is the input, it generally receive the output in opposite phase. We can say that it is out of phase. Out of phase. Okay, so it is generally out of phase. Whatever input is there, the output is in out of phase with respect to it. Then comes to our main part, that is our integrated circuit voltage regulators. Okay, so this section generally deals with our integrated circuits, or whatever things we have seen here. If you substitute the MOSFET in case of IC, it similarly acts as the devices. Voltage inverter IC configuration. Here all in the above also step up IC configuration. Similarly, if you replace it the MOSFET with a IC, it also behaves as the same. Here the integrated circuit which we use in case of the MOSFET or op-amp have several types. Okay, several types of both linear and switching regulators, because in whatever arrangement we have seen in case of linear switching regulator, we just have to replace the arrangement or the main differentiator with respect to the IC. So in the linear regulators are the three terminal devices which provides the output, the input, and the other terminal can be made to the linear differentiable or differentiator which can be grounded. So the linear regulators are three terminal devices. It provides either positive or negative output voltage, which can be either fixed or adjusted. Fixed if the IC is fixed, if the IC is taken having a fixed value, so the output can be fixed, and if it is not fixed, then it can be make use of rheostat so that it can be adjustable. The first is our fixed positive linear voltage regulator. Here also IC is used. Okay, so here you can see here it is a example of IC regulator, that is 78XX. Okay, so it is three terminal devices which are input, output, and other act as the ground voltage. Okay, so here as you can see 78XX, the last two digit is generally refer to as what will be its output voltage. It refer to its output. If it is 7810, okay, so the output voltage gives 10 volt, as you can see from the tabulation below also. Okay, 78XX 7812 means the output voltage is 12. 7818 it's 18 volt. Okay, so whatever it is a series, Okay, if you can take anything, it is a 4-digit series. 78 is the batch name, and the last 2 digit shows the output voltage. What voltage should be given out from the integrated circuit in order to make constant voltage supply. Again, the fixed negative voltage regulator. Here the 79XX, the 79 is the batch series, and X and XX is the same output voltage, but here the difference is that it is negative means what? Whatever input is there, the output is in out of phase. Okay, therefore it is negative. So it is a fixed negative linear voltage regulator. It is a fixed negative voltage regulator. It is a 3-terminal device which are input, output and ground, as you can see from the figure also, and here also it is the boxes. Next comes our adjustable positive linear voltage regulator. The series given here is LM317. Okay, so it is a regulator, a positive regulator. It is also a 3-terminal device making out of input, output and an adjustable terminal. As you can see, it makes the different from the above two. There is an adjustable terminal or the adjustable arrangement. The whole it is the adjustable arrangement. In the previous one there is ground, but here it is the adjustable terminal consisting of two resistors which are shunted or in make arrangement, and there is a capacitor which is attached series in series formation. So here LM317 can vary its output from 1.2 volt to 37 volt. Okay, there is no common specification for number. Generally, a particular series is variable to this order. If it is another series, then it can be followed another suitable values. So the LM317 adjustable for our positive voltage regulation. Here the capacitors are for decoupling. You can see decoupling means whatever signal it is applied, whatever signal is applied, it can't be transmitted or it can't be coupled because it is already grounded. The C2 is already grounded. So capacitors is not meant for coupling, rather for decoupling, and it do not affect whatever the operations, the DC operation going on. The resistor R1 and R2 in output section is used to adjust the output, and where R1 is fixed, R2 is adjustable, and where R2 is fixed, R1 is adjustable. They use the vice versa function. So here the reference current is equals to the voltage reference divided by the initial resistance R1. Okay, if it is fixed, if R2 is fixed, then you have to replace it with R2. Okay, mind that. So it will become, it is nearly around 1.25 because it will take half cycle. Why it is 1.25? Because we have to divide the factor with respect to 4. Okay, because you have to divide the whole output. Suppose it is 5. 5 divided by 4. Okay, or with respect to multiples of 5 and times divided by 4. So it will receive the 1.25 volt because the minimum output it will be provided is 5, not less than 5. So minimum is 5 volt. So then the output can be referred to as the reference output. These things also already discussed in the previous series regulator or switching regulator. The extra part is our adjustable component, that is IADJ, which can be received through the load R2. Okay, and the L71 is a floating regulator because the adjustment terminal is not connected to the ground. Floating means it can be varied. Then comes to the adjustable negative linear voltage regulator. You can see the same arrangement, but only difference is that the condition is for negative linear voltage. The only difference is that. Okay, so L337 is the series name for the negative. You just have to remember 2 to 3 names for the linear voltage regulators. It is an adjustable negative linear voltage regulator like LM317. It is a 3-terminal device and 2 external resistors for output voltage adjustment. Okay, so the L337 can vary its output from these things. We have seen the same for the positive. In case of positive, it is plus 1.2 volt to plus 37 volt. In case of negative, as the series is nearly same for LM, so it is minus 1.2 volt to minus 37 volt. Okay, so this is all about our integrated circuit regulators. We see how it can be, how the switching and linear regulator can be replaced with respect to integrated circuit IC, or if we made the integrated circuit regulator as usual, it can be divided into four types. There is adjustable negative, adjustable positive, there the fixed negative, and there is fixed positive. Okay, though it is as it is appeared as a very small question around 4 marks, so you can easily interpret it. You only have to remember the circuit diagrams, which will be more flexible or beneficial for you all. So this is it for students. If you have any doubt, you can put your question in the comment section. Thank you.